Okay, so hi everyone. My name is Mayan. I'm working Robusta. First, I want to say thank you for joining us for our first webinar. So it's very excited. This is going to be the first webinar from a series of webinars we are going to do about Kubernetes. We are already planning the next one, so follow us to get more updates. Our speaker for today is Or, a senior developer from Classiq, and also Nathan, the CEO of Robusta, is here with us. So we can start. Or, is yours.
Hi everyone. I'm very happy to be here today. So a little bit about me. I've been in Classiq for about a year and a half. During this time, I've been deploying Kubernetes to production. I've been using Terraform, and I've even recently started using GitOps with FluxCD. I'm a member of the infrastructure team. We do basically everything infrastructure. We do code infrastructure, developer experience, and DevOps, which is the reason we got here today. My background is mainly in software development. I've been a software developer for about 10 years now. And that's about it. So what are we going to discuss today? First of all, I'm going to introduce the Classiq platform. It's not a promotion. It's just for you to understand where I'm coming from, what are my constraints, what informed the problem I'm trying to solve, what considerations do I have, what constitutes a good solution, what constitutes a bad one. Then we're going to iteratively go through several solutions to the problem, improving gradually, and to see the trade-offs and how the solutions improve. And then finally, we're going to conclude with future work, things that we can improve even upon the current implementation. So let's go on. So the Classiq platform is a quantum software platform. Unlike hardware platforms, hardware companies which focus on building the best quantum computer there is, we focus on the algorithm development process. We provide a modeling environment that allows the developer or the researcher in this case to design a high-level algorithm. Then we compile the algorithm down to low-level instructions, just like assembly. But the process, unlike classical compilation process, is much more computationally demanding. It's not just, you can call it a polynomial process that takes a computer program and translates it to assembly. It has to fit the logic into a very, very tight set of constraints. We have a limitation on the number of bits we can use. We have a limitation of the number of instructions we can use. So we basically solve a constraint satisfaction problem, which is NP-complete, and it takes a lot of computational force. Once we compile the algorithm to low-level instructions, we can also now execute those instructions either on real hardware or on a simulator. And similarly to the compilation step, also the simulation is also very computationally demanding. So our problem is that we have two very computationally demanding steps that we want to offer our customers as a service. We want to be able to compile their models into concrete implementations, and then we want to be able to simulate those implementations on our platform. During this time, we also want to keep our servers responsive. We can't just dedicate our servers to handle these requests. We also need other, you can call them maintenance or administrative requests to be handled while we execute those long-running jobs. And we also want to be able to execute, to auto-scale our compute resources on demand. If we have a burst, we want to be able to scale up. But once we're done with this burst, we also want to scale down so that we have a reasonably sized deployment. Now, the first version of the architecture is a pretty simple one. We have a statically sized deployment, and we use WebSockets to keep the connection open for the entire duration of the task. So if we take, for example, 30 minutes or an hour or even more to compile a circuit, we have to keep the connection open for that entire duration. And that's not that good for several reasons. The first one is that we don't have dedicated compute resources. We have one type of compute resources that handle both requests and the long-running tasks. Our tech stack is based on Python, and Python multithreading is not that great. And even if you have multithreading, you don't want to open too many threads on your Kubernetes pods. Next thing, we don't have autoscaling. Our deployment is statically sized, so we have a fixed number of pods. And finally, because we keep the connection open for so long, the entire situation is very, very flaky. If the user has bad Wi-Fi reception, if the user closes their client for some reason, they lose the entire progress. And if it's an hour worth of progress, the loss is significant. It hurts the user experience significantly. So what can we do to improve upon this? The second version of the architecture introduces Redis as a job worker. Redis here serves two purposes. It first holds the job details, the task details. What kind of task do we plan to run? What are the arguments for the task? What is the execution result once we're done? And second, it holds the task queue. Which tasks are do we still need to run so that the workers can query both of these, can query both of these. Now, we also separated our compute resources. We have now dedicated resources for the API servers, and we have dedicated resources for the workers. So we now have significantly better responsivity, because now the longest task that the API servers have to handle is submitting jobs to Redis. Everything that is longer than that can be replaced by submitting the job to Redis. And second, because the requests are now much shorter, we no longer encounter the flakiness issue. Now we can, if we close the client, we can now just resume querying the same ID, and the job will still be there. We didn't lose any progress. What issue we didn't solve yet? We didn't solve the autoscaling issue. We still have statically sized deployments, even if we put aside the API servers for now, because they aren't that computationally demanding. We want to be able to autoscale our workers deployment. Now, what can we do to solve this issue? If you Google autoscaling, Kubernetes autoscaling, the first result, and I checked it yesterday, I think, is the horizontal pod autoscaler. And we chose not to use it. As a general rule, I'm all in favor of using the default solution when it's suitable. I Google it, I check out the first results in Google, and if I don't have a very good reason for it, a very good reason to do otherwise, I use this solution. But unfortunately, in this case, the default solution didn't work for us. If we look at the scale-up scenario, the horizontal pod autoscaler is usually utilization-based. It looks at the compute resources, the CPU, the memory requirements of your pods, and then it decides to scale up or scale down the deployment. It also has an API for custom metrics, but it's much more involved than we would like it to be. This was too inflexible for us. But the main point of pain here is the scale down scenario. Because the way the horizontal pod autoscaler works, which is changing the deployment size, the scale down part is managed by the Kubernetes scheduler. The Kubernetes scheduler decides which pod to terminate. And if it terminates a pod that is currently mid-job, again, we're back to the scenario of losing progress, which we definitely don't want to do. We want the ability to let the autoscaler to choose for the autoscaler which pods we want to scale down. We don't want to scale down arbitrary pods because that way we lose progress for our users. So we have to find another solution. And in this case, our solution is KEDA. KEDA includes it's a product. It's you can call it a thing that you install on your cluster using Helm, and it includes several things. It includes CRD, several CRDs, and it includes an operator that uses these CRDs to scale up or down entities on the cluster. Now, the main CRD we're going to focus on is the scale job. It's the main CRD that KEDA includes. It is a template for jobs the same way that a deployment is a template for pods. You specify a template, and then KEDA can observe, can use the scale job template in order to produce how many jobs it deems necessary. And those jobs in turn contain the pods, and those pods execute the code we want them to execute. Now, how KEDA knows how many jobs to spawn? It has multiple options for triggers. It can scale out on many events that pretty much KEDA's main selling points, that it is an event-driven autoscaler. It's a Kubernetes event-driven autoscaler, in fact, KEDA. And you can point the scale job to pretty much anything that you want and use that as the counter for how many jobs you want to spin. In our case, we chose to point KEDA to our Redis deployment and point it to the specific key that houses the job queue, the task queue. And now KEDA can observe this key, which is a Redis sorted set. It can tell its size and then use this size to spin up more jobs. And each one of those jobs execute one of our worker pods. These worker pods pull resources from the tasks from Redis until they are idle. Once they're idle for long enough, and we see that we are done with our job burst, that our compute resources are too high for our current demand, we can scale down. And the scaling down is done by the worker committing suicide, by killing itself. This way, the party responsible for scaling down is not an external scheduler, but the pod itself, the worker itself, which is the best entity to know if it's idle or not, if we have too many compute resources or not. So this way, we can guarantee that we don't lose progress. We might sometimes scale down too fast, sometimes we might scale down too slow, but we can definitely be sure that we didn't lose any of our user progress, which is our main priority.
Or would it be all right to step in with a question here?
Yeah, of course.
So if I understand correctly, then you have you had these jobs you had these tasks, that came in from all the clients, and you put these in Redis. And now in that Redis queue, you have a whole bunch of work items, right?
Yeah.
And you then define a KEDA scale job, and that spins up a bunch of jobs to handle the stuff in that work item. But each one of the jobs that gets spun up, it's not assigned a specific work item, right? You're just scaling the number of jobs according to the size of the queue right now.
Yeah, I'm scaling the amount of jobs based on the size of the queue. And each one of those workers aren't assigned a specific task. They can pull tasks from the queue until the queue runs out. KEDA isn't in charge of the task distribution. It's only in charge of assigning, scaling up or scaling down the compute resources. The workers themselves are responsible for distribution, together with Redis, of course.
And then the reason, to elaborate on this a little bit, I think I know the answer here, but can you maybe speak a little bit about, like, okay, why is this a job then, not a deployment?
The main issue, a deployment, first of all, KEDA pretty much the main thing that KEDA offers is a scale job, first of all. And the second thing is that unlike a deployment which holds alive for perpetuity, ideally, unless one of them starts, a job can start and end. And in this case, a job terminates when it has been idle for long enough. It is okay for a job to terminate. It's okay for workers to scale down. We in fact expect them to. While deployments see changes to the deployment size as a problem that requires fixing, a scale job doesn't.
That makes a lot of sense.
Yeah. Not the deployment size, I'm sorry, the amount of pods currently running. The deployment size can be changed, and that in turn triggers the changes to the amount of running pods if we want to be really nitpicky.
So if I summarize, like if I put this, I'm trying to put this into my own words as well, so to make sure I understand. If you're using a deployment or you're using a scale job with KEDA, right? Then when you have a bunch of work items that come in, the scaled up process probably looks similar, but the scaled down process for the deployment, it only scales down when you externally scale it down. And then you might scale down also when there's still stuff that's being worked on.
I won't scale down mid-job because each individual worker won't scale down mid-job because the worker itself is responsible for termination. The scale-up process is similar to deployment if you look at at the list of pods that are currently running, but it is a little bit different because it is informed by an application level metric. It isn't based on utilization. It isn't based on something that is Kubernetes native. KEDA actually knows the name of the specific key in Redis. It knows where the Redis server is located. It has to know all of these things so that it can scale up based on information that is derived from the application, not from treating the workers like a black box.
Okay, thank you. Yeah, that makes a lot of sense. And this is just a reminder also for everyone else here. You can leave questions in the comments, or we're trying to address them as well.
Yeah, we'll also leave time for questions in the end. Yeah. Okay. So what did we gain from all of these architectures? We gained the ability to execute long tasks while using short-lived requests. We also gained the ability to respond to those short-lived requests in time. We separated our compute resources from our servers. And finally, we gained the ability to auto-scale based on demand. While in this process, we also gained a few things that we didn't plan on gaining. We gained the ability to use dedicated hardware for robots. Because we use EC2 over EKS, we can allocate specific instance types for specific pods. And in this case, we chose more, you can call it beefier instances to execute the more computationally demanding workers. For example, we use burstable instances for our servers, which makes a lot of sense, but we want non-burstable instances for our workers, which has more consistent and demanding CPU requirements. We also have the ability to execute to use multiple task queues. Once I have one task queue, I can have several of them, and we can specialize each of the task queues for a specific need. We can have a task queue that is specifically for GPU-related tasks. One of the simulators that we use is GPU-based, so we can spin GPU instances and have those instances run tasks, and we can spin those instances only when we specifically need to execute those tasks. Because GPU instances are expensive, we can use KEDA and the cluster autoscaler to make sure that we don't have any of them running until we actually need to. Additionally, we can fine-tune the memory requirements, the memory and CPU requirements for just plain workers, so that we'll have, if you have, for example, medium-sized job, you will allocate such and such amount of CPU and memory. And if we have larger jobs that require even more CPU and memory, we'll have a dedicated queue for them, and we'll spin up larger and more demanding pods only when we get those kind of tasks. This allows you to utilize your cluster and your compute resources much better compared to just to not using several task queues, not using a job worker. And that's about it. What can we do in the future to improve upon this? The main thing that we lost along the way of improving our architecture is that we gained more complexity. We have more things to manage. We have, for example, now CRDs, we have an operator, we have multiple jobs, we have another deployment, and all of those things require managing, they require configuring, and they can be misconfigured. This means that we need to monitor the logs, need to monitor the metrics, and we also need to monitor Kubernetes, which is helped a lot by Robusta's product. Additionally, because we introduced non-trivial dependencies in the cluster, we hurt the development flow. If our deployment would have been vanilla Kubernetes deployment, it could have been installed on, for example, if you spin a kind or a minikube cluster on your local machine, you can install our deployment there and just test, for example, changes to the way we deploy our application to our Helm chart. But because you have non-trivial requirements, you need to have non-trivial setup. You can't just install them on a vanilla Kubernetes cluster. This means that you either have to set up your own cluster using some non-trivial steps, or you're forced to use a remote environment that already has all of those things installed. And both of those things can be improved upon, and we are actively working on making them better. And that's about it. And now I'm available to any questions that you might have.
I'll say in the meantime, and if you have a question, please feel free to either write in the chat or just take your mic off, and then I'll also see that you're ready to talk. Thank you, and this is fantastic. I mean, I think for me, it was very interesting to also see not just the solution you chose, but also how you arrived at that really by iterating through other solutions and where the old solution fell short. So for me, that was, I think, the most interesting part. Do we have any questions from the crowd?
Yeah, I have one question in the, how does the worker takes the load from the bucketing? So let's say you have 100 requests in the queue on the Redis side. So there might be one part, it will be taken from 1 to 10 requests, and next part has to take from 10 to 11, right? So how are you splitting the request on the worker side?
I think I've lost some of your question, but the way that they take questions that they take tasks from the queue is that they have this is managed by a library that we use. We have a Python library that is built upon Redis. It's called ARQ. The way this library works is that you have a sorted set based on the submission time. This allows you also to execute deferred job. You can schedule jobs to be executed in the future. And each of these workers go over the sorted set and try to pick onto that sorted set. Once they see that they have a task available, they start executing this task, and they add another key to Redis that is an empty key. Just the important thing here is the key itself that says that this task is in progress. Once you have a task in progress, other workers won't try to execute it. I hope I answered your question.
Thanks, man.
But just to summarize, it's this is a part of the application level. It's not part of the you can call it, it's more of a dev problem than a DevOps problem. You can take out the specific job management system that we use and plug in another one, and KEDA would be able to handle it pretty much just as well.
So I have a follow-up question to Rajesh's question then, right? So what you're saying is the application, it goes and it just pulls stuff on its own, and then it marks it as in progress. Can you have stuff that goes missing? Like if one of the pods starts working on something, and then that pod ends up dying for some reason out of your control, can you end up with stuff that's marked as running but never actually completes?
That's, again, I can answer that question, but I can't take credit for the implementation. It's also implemented by the library that we use. The in progress, each of those tasks have a timer. We defined a maximum time that the task can take, and once the task goes above this time limit, it has considered to be failed. And one of those, the way it can fail is for the pod to die without marking any result. In this case, we use one of Redis, I think most useful feature, which is giving a key an expiration date. The key is marked to be expired at the specific timeout. So once you pick so once this time passes, if the task is still in the queue because no worker has actually finished working on it, then it won't have the in progress key as well, and new workers can start working on it.
Cool, that makes a lot of sense. Do we have any?
Yeah, we have a question for Jasper.
Yes.
The question is scaling the amount of jobs to 0. It's possible that the queue is empty for a while. Yeah, it's possible. For example, in this case, you have 2 ways to go. And we implemented both of those ways to different scenarios. In one case, we can have for example, on GPU machines, we want these machines to scale to 0 if we don't have any jobs. So we let the amount of workers scale to 0. We no longer have pods that use these machines. And so the Classiq autoscaler, which is independent of KEDA, sees that there are no longer pods that run on the machine and scales it down. This is one solution. The other solution is, in addition to the amount of scale jobs, we also set up a deployment. Static site deployment, like in the second version of the architecture, that provides us with a minimal amount of workers that is also always up. This is done to prioritize responsivity not only to requests, but to tasks. If we, for example, have a small amount of tasks, we want the ability to respond to them quickly, especially if those tasks take a relatively short time to execute. For example, they take a few minutes. A few minutes is too long for the API server to handle itself, but it's also too short for us to scale up something just for it. So for this reason, we keep a few running workers just to respond to, you can call it the background noise of jobs. I hope that answers Jasper's question. For Rajesh, you can track the job relay. You can track it. You also have some sort of, here you have several levels of tracking. If it's an application related failure, you can, you pretty much have the information in Redis, and this is handled by the application. The library also supports a set amount of retries. You can configure for each job type how many retries it does on a specific job before it gives up. And those retries will happen independently of what's the reason for the job failure. If you want to be more specific, for example, let's retry on an kill, but not on an application level failure, then you have to involve some sort of an external monitoring. You have to have something that monitors kill events and then resubmits the job or does something similar, which we didn't implement yet. I'm not sure we have a current plan to implement it, but it's an interesting way to go. And again, maybe Robusta or KubeWatch, which is a part of Robusta, can help use this. Can help implement this solution.
All right, that's call for questions before we wrap things up. Okay, so I think we'll call it a night. A huge thank you, Or. That was fantastic. I knew a little bit about what you guys are doing, but now I feel I really have the big picture, and also I learned a few things about KEDA. I think I speak for everyone here that it was really interesting to see the architecture that you built. So a huge thank you, and thank you to everyone who joined us and participated. Maayan, any closing words on your end?
I also wanted to say I was very happy to be here, and I was very happy to kick off the great initiative of having Kubernetes Tech Talks on more advanced topics.
It's our pleasure. And I see Rajesh also asked if you can share the slides afterwards.
I'll send them over to you. Yeah.
Fantastic. Send them to Maayan. We'll send out an email afterwards.
Yeah, I will share the recording also in the events, and we are going to have it on YouTube. So that's it. Thank you all. Thank you, everybody. Thank you all.
Thank you.
Take care. Have a wonderful night.
Bye-bye.
Bye. Thank you. Good night.
Good night.